What is the Jacobian and where does it come from? Before I start, I want to look at kind of an intuition from single variable calculus, which if you're watching this video, you're probably familiar with. So I have this integral here, and one process that we might very well do is do a u substitution. So if we take that and set it equal to u, take the derivative of both sides, and then solve for dx, then we see that we can replace dx with 1 over 2x du. So we're replacing this with this. And this is something you could kind of think of as the Jacobian. It's just nothing more than a multiplicative factor that allows us to change the variables. It kind of justifies the change in variables or equalizes the change in variables. So that's the importance of the Jacobian. The other thing I want to look at is that the magnitude of the cross product of two vectors equals the area of the parallelogram formed by the vectors. And so if you have vector B and vector A, and you want to find the area, well, the area of a parallelogram is base times height. So we can use this for the base, magnitude of vector A. And then for h, I know that sine of this angle is h over magnitude of b. So here that is. If I solve for h, I see that I can replace h with magnitude of b times sine of the angle. So we have that here. And then it's also well known that this is equal to the magnitude of the cross product. Now, I'm not going to go into that in this video, but I do have a video proving this is equal to this, and I will put that in the description. I'll put a link in there. But I just want to highlight this before we continue on because that's key to this whole video.
If we had a double integral and we didn't want to take it in the xy plane because maybe it's too difficult, then we could use another grid system UV, which I've superimposed over here. And of course, a movement in X would require, to go to the UV world, it would require, U movement and V movement. We can see that here. X would be dependent on UV. Y would be a function of UV as well. And then you'd have your du dv and the Jacobian that makes it possible to get to here from here. This grid wouldn't have to be, these wouldn't have to be right angles, of course. It could be like this, just long as there's only two directions. But anyway, so to get from xy to uv, and to do the integral, we want to think of how we would form these vectors. And then once we have the vectors, then we can take the magnitude of their cross products, and it would give us the area of that parallelogram. So here I've tilted the box so that the u and v are vertical and horizontal, and the x and y's are diagonal. And to think how we would, form this little dx vector, we could think of algebra 1. So y equals delta y over delta x. And well, we could look at that first. Obviously, that's true. If we multiply both sides by x, we get that. And that's just basically the equation of a line. And from that, we basically get the multivariable chain rule. We could put, d's in front of the x and y, and that would be perfectly fine. So since we have two dimensions here, two independent variables, then a change in z, the differential, would just be these two things. So hopefully you're kind of familiar with that if you're looking into the Jacobian. Well, anyway, to form this x vector, a change in x would require a change in v plus a change in u, and same with vy, it would be this plus this. And so basically we get these. So to go from the x world to the uv world, we would need these two parts, same with y. So these basically are the two vectors that we need. Just a little FYI, you could also write this in matrix vector form, and this would be the Jacobian. The Jacobian matrix transforms from the UV world to the XY vector world. And so I just wanted to point that out, but we're not really using so much the Jacobian matrix as its determinant. So as we go on, you'll see that we're actually taking the determinant of this matrix. What I did here, I just took the two vectors and wrote them in, this form, added a little color to make it easier on the eye. I changed these to just vector A and vector B, and now we're ready to go from here. Okay, continuing on, now we just need to take the cross product and then its magnitude, and we'll get this area of our formed by the parallelogram of our two vectors. So if you're shaky on the cross product, I'll put a link in the description to a video on the cross product. So I'm kind of assuming that you kind of know about that. But anyway, we have to go to 3 dimensions because to do a cross product, we need 3-dimensional vectors. So we form them with dummy zeros and stuff. And this is the standard way to do a cross product of two vectors. And so when we do that, we're going to get another vector, and it's going to be a one component because these zeros got rid of the ij directions, but this is still a vector with you'd have 0 0 over here, and then the third component k. We don't care about the direction, the k unit vector, we just need this thing. So moving on here real quick, we're almost there. So I just wrote this vector like this, and I put the zeros back in there for clarity. Now we're just going to take its magnitude. I'm guessing you know how to take the magnitude of a vector. So we're doing that here, and this is it. So this basically gives us the area of this thing. But we want to sort out the Jacobian so we can see it specifically. So if we factor out the du dv, then that's here, and this is the Jacobian. So this is what we wanted to derive. It's convenient to package it, though, as a determinant of a 2x2 matrix. So, because most everybody knows a determinant would be this times this minus this times this, which is exactly what this happens to be. And that is the Jacobian. One thing I would like to say real quick, though, is you do want to have the denominators lined up vertically, because you could say, well, to do this times this minus this times this, well, these could have been switched, but and the determinant would still work. But I still recommend keeping similar denominators lined up vertically, because you'll notice that using the matrix, that has to be the case in order for the matrix to be able to multiply the vector. So if you just always do that, it's a good thing. It'll make sure whether you're using the Jacobian matrix or the Jacobian determinant, nothing's going to go wrong.
In closing, let's think why the Jacobian works so well to go from rectangular coordinates to polar coordinates. You may know that you have to put r in front of the dr d theta, and this is the Jacobian. R is the Jacobian, and you can figure that up. I've done it here. I'm not going to dwell on it. You can verify, but if we just think of u and v as r and theta, and we use these properties and go ahead and figure up these four things, and then put them into the determinant of a 2 by 2 matrix. Go ahead and do the determinant. Here, the cos squared plus sine squared is just going to equal 1. So you factor out the r, so r times 1, you just get r. And there we go. But we could also think of this in a different way. Let's think about what's the area of a tiny piece of the polar coordinate system. Well, we know that that is just going to be a tiny piece of radius. And what would this be? Well, that's just an arc length, and we know arc length is equal to radius times angle. And so this is going to be radius times an infinitesimally small piece of angle. And so we get an area that is r dr d theta. And then if you're thinking, well, how can this turn into a rectangle? Well, as r and theta go infinitely close to 0, these are already the same length, and these get so small they don't curve anymore. They imitate straight lines, and they also get infinitely close in size to each other. So it doesn't matter if bigger in this area if we had thought about this arc length or this arc length. And so, interestingly enough, as we go infinitely close to 0, we get a tiny, perfect rectangle, unlike the one I just drew.